Hello students, welcome to the course of Mechanics of Machining. This is the 12th lecture. Today I am going to discuss thermal aspects in machining. By thermal aspects we mean we will find out how much heat is generated, what is the temperature. Heat is always generated when mechanical energy is converted into heat. Some type of mechanical energy conversion takes place, and the heat may be generated in machining at three places. It can generate in the shear zone, here it is generated, and heat can also get generated at the tool chip interface, because the chip is moving on the rake surface of the tool. So, there is a lot of friction. That frictional work gets converted into heat, and then tool may rub against the workpiece, against the machine surface, like it is work tool interface zone. Here also the heat is generated, and this figure shows the source of heat in machining. Now, about 80 to 85% heat is generated in this particular zone. That means, where actual plastic deformation takes place and chips get separated, that in that area 80 to 85% heat is getting generated. Due to friction on the tool rake surface, when the chip is sliding, then about 15 to 20% heat is generated, and here there is very small amount of rubbing, and that is why here the heat generation is about 1 to 3%. Now, what are the main variables that affect the cutting temperature in that particular order? One is the cutting speed. Cutting speed is the most important variable. Suppose we increase the cutting speed, then the heat generation will increase, and accordingly the temperatures will also increase. So, cutting speed is the most crucial parameter. Number 2 is the cutting feed. Feed also, if it increases, then the temperature will increase, but feed's effect may not be as much significant as that of the cutting speed. Then depth of cut also has some influence on the cutting temperature. So, it is found that whenever the heat is generated, out of that heat about 80% heat is carried away by the chips. Chips fly, so they carry away. You might have seen in the workshop that when you are machining some metal, then the chips are actually flying and they almost becomes red actually. It as if the fire, in some cases like a spark, they are flowing. In some cases that temperature may not be that high, and those chips also become sometimes blue color, sometimes little dark blue color, because of the oxidation at that high temperature and lot of compounds formation. So, 80% heat is carried away by chip. That is a good point. So, that is why maybe tool will not get that much damaged, but 15 to 20% heat also goes into the tool, and that raises the temperature of the tool. And as you know that once the temperature of the tool increases, then its hardness will slightly reduce. That is, hot strength of the tool may reduce. So, that so we have to do something to cool the tool, and 5% heat also gets conducted to the workpiece, and it raises the temperature of the workpiece. Now, raising of the temperature of the workpiece has two main effects. Sometimes if the temperature increases by a large amount, then the workpiece may undergo expansion and it may affect the machining accuracy. And another effect is that because the temperature increases, so flow stress of the workpiece reduces and it eases the cutting process. So, tool temperature is influenced by properties of workpiece material, since they affect the size of plastically deformed zone and the chip tool contact area. So, workpiece material is important. Some tool, if it is machining soft material, the temperature may not be high, and if the same tool is machining hard material, then its temperature may become very high. So, that is one thing, that what type of work material you are machining, that will have effect. And tool geometry and cutting fluid etc. are other factors that influence cutting temperature. Tool geometry also has some significance. We have already discussed it in our previous classes, and cutting fluid also has effect. So, that is why we have to use cutting fluid or coolant. Now, why do we want to know the cutting temperature? This is the natural question. So, one answer is that to know the machining performance, whether machining is being done properly or not. Ideally, we do not need much temperature generation. If machining performance is not good, sometimes you may get very high temperature. Second thing is that we design and select the cutting tool based on how much cutting temperature is generated. Cutting tool has to be designed to cope up with that temperature. Then we can find out the thermal stresses with the temperature, and also materials flow strength depends on the three main factors. One is the strain, other is the strain rate, and the third is the temperature. So, there is a famous Johnson-Cook's equation that I have written. It is based on the Johnson-Cook model. Here tau is the shear strength. This tau is the shear strength, and this is 1 by root 3 A plus B epsilon n. This is strain hardening component. It indicates that if strain is increasing, then the strength is increasing. Other is the strain rate effect, 1 plus m is some constant depending on the material, and this is logarithmic. Epsilon dot divided by epsilon dot 0. Epsilon dot 0 is some reference temperature. You can take 1 into 10 to the power minus 3, and epsilon dot is the strain rate whose unit is per second. So, strain rate if it increases, then its shear strength will increase, and the temperature also if it is increasing, then the strength is decreasing. Temperature has opposite effect to that of strain and strain rate, but this is the formula given. So, if you want to precisely model and find out the forces etc. in the machining, then we must know the proper value of the flow strength, and for that purpose we must know the temperature also. So, that is why we need to estimate or measure the temperature. And another thing is that when the chip separates, when the chip will be separating, when there will be some amount of fracture, and most of the time it is ductile fracture, particularly if the material itself is ductile. In that case, there is one critical strain, that is epsilon f, and d1, d2 etc. are constant parameter, and this sigma m is the mean stress, sigma eq is the equivalent stress, and this is 1 plus d4 ln epsilon dot 0, and then it is T minus T0, Tm minus T0. So, that means this is showing that your strain to fracture will increase depend if the temperature increases by these parameters, and this relation is there. So, this type of damage model we have got, by which we can find out the critical strain, but we need to know the temperature also. So, temperature plays a role in both of these equations. Now, let us understand that how we find out the temperature or how we do the heat transfer analysis. We assume that most of the cases may be convective heat transfer, and radiative heat transfer will be very small in comparison to heat transfer by conduction. So, we first develop that heat flow due to conduction. So, we can use Fourier's equation. Fourier's equation is what? Qx is equal to minus Ka d theta by dx, where theta I am indicating by as a temperature. Theta is the temperature that symbol I am using, because T may confuse with time also. So, Q is the rate of heat flow, K is the thermal conductivity, A is the area of cross section normal to x direction, theta is the temperature, and d theta by dx is temperature gradient. Why we are having minus here? Because if the temperature gradient is negative, then heat is flowing in that particular direction. So, this is the basic Fourier's equation, but we can make a cube actually, and in that heat is flowing in all directions. that is it is flowing in the x direction, that is indicated by qx. It is qx this side and qx plus dx this side. Then we have qy and this side we have qy plus dy. Then on this face qz is entering and from other face qz plus dz is coming out. And the temperatures are also indicated here. If at the center the temperature is theta, then we can have theta plus del theta by del y into dy, or we can have this as a reference point. If this is the origin, then in that case this equation becomes very proper, that this is theta plus del theta by del y dy, and here also it is theta plus del theta by del x dx and del theta by del y dy plus del theta by del z dz. Okay. So, this up to first order approximation, these quantities have been written, and so for this element of dimension dx dy dz, the Fourier's law of heat conduction along x direction is given like this: qx is equal to minus k dy by dz, because area normal to the x direction is dy by dz. And according to Taylor series expansion, if we neglect higher order term, then qx plus dx can be written as qx plus del x into dx, and this I can take qx, I can take from here, and then I can write it like this. This equation becomes like this: dx dy dz. So, qx is the rate of heat flow into the element in x direction, and qx plus dx is the rate of heat flow out. So, that is why its sign has to be different. So, net heat flow due to heat conduction along x direction is qx minus qx plus dx, and this becomes this quantity dx dy dz and this quantity. Similarly, net heat flow due to heat conduction along y and z directions are given like this. In the similar way we can write, and qz minus qj z plus dz is equal to this. So, these expressions we have written. Now, we have to see the other component. Actually, suppose some material is moving, that means transportation of the material is also taking place. Suppose it is a hot material and it is passing, naturally it is also transferring some type of heat. So, heat flow due to transportation is discussed here. Here this expression is q dash is equal to rho Cv A into theta average. Suppose the average temperature is theta, and rho is the density, C is the specific heat, and V is the velocity. Then rho C rho into V, that will give heat flow, okay, per unit time, and C is the specific heat. So, heat flow due to transportation along x direction can be calculated like this: qx dash x is equal to rho C Vx, and this much quantity we can write, and similarly q dash x plus dx is equal to rho C Vx, this one. So, net heat flow due to transportation is actually written as along x direction is written as is equal to this much q dash x, because this heat is entering and this heat is coming out. So, that means heat entering is rho C Vx and this much expression, and heat coming out is this. So, the net heat flow is minus rho C Vx del theta by del x dx y dz, like that. So, similarly, the net heat flow due to transportation along y and z direction is given like this, and that expressions are there. Then we have to see how much is the heat is absorbed by this element. So, heat will be absorbed if the temperature of the element rises. Suppose the temperature has risen by some amount, let us say by delta theta. So, rate of rise is delta theta by del tau, where tau is the time. So, rate of heat absorbed by the element of dimension dx dy dz, qa is equal to rho dx dy dz times c, c is the specific heat, and del theta by del tau. Here you can see that this rho is the density and dx dy by dz is the volume of that element. So, this quantity is total mass of that element. That mass is very small, but this quantity also has to be added here, and then this is the rate of heat absorbed due to temperature increase. Then heat generated. There may be heat generation in the element. Heat generation may be due to various reasons, particularly in machining it is due to plastic deformation. When plastic deformation takes place, then most of the heat, in fact at least 90% heat gets converted into the heat. 90% plastic work may get converted into the heat, sometimes it can be 95% also. So, that heat generation is indicated by Qj is equal to Qg is equal to Q dx dy dz, where Q is the rate of heat generated per unit volume. So, if we put that thing, balance of rate of heat flows gives like this. I am putting all type of heats here, heat due to absorption, heat due to generation and all these things. So, whatever there has to be heat balance, that means whatever heat generated or whatever heat has been pumped into the element, heat generation plus whatever heat has been pumped into the element, both would sum to the heat absorbed. Then only there will be proper heat balance. So, if we substitute these quantities, I am skipping lot of steps here, you can put all those values together, then you can get this type of expression. So, we are getting K rho c, and this is del square theta by del x square plus del square theta by del y square plus del square theta by del z square, and minus because of the velocity effect, because of the transportation of the material, and plus q by rho c, and this is del theta by del tau. This is a 3-dimensional transient heat conduction equation. If the material is not moving, then this second expression with a negative sign will not be there, and in that case you will be getting these two terms. And similarly, if it is a steady state heat conduction, then del theta by del tau will be 0 and this will become like this. So, you will be getting this type of expression. Now, as we know that K by rho c is known as the thermal diffusivity. It is the thermal diffusion, how fast the heat will diffuse into the material, how fast it will be moving. Suppose K is very high, that means material is highly conductive, then immediately heat which is on the surface will immediately go to the interior part, it will move to the other side because conductivity is very high. So, that is why diffusion will be fast and it is inversely proportional to density and specific heat. So, this is called alpha, and K by rho c has got a unit of meter square per second. Now, so this expression is the basis, we can solve this either analytically or numerically. So, let me just now discuss again that what are the main heat sources in metal cutting. Main heat is due to plastic deformation. Due to plastic deformation, work will be done, and that energy of the plastic work, when we do the plastic work, that means we supply the energy. So, that plastic energy that will be converted to thermal energy in some proportion, means it is not necessary that 100% plastic work is converted into the thermal heat. Some portion may be stored as internal energy like in dislocations, etc. So, thermal energy is given by some Taylor-Queeny coefficient into plastic energy. This coefficient usually lies between 0.9 to 1. Taylor-Queeny coefficient is lying between 0.9 to 1. Some people use symbol eta for this. Okay, some people use symbol eta. Otherwise, means there are different symbols, but mostly eta is used. So, that means 90%, at least 90% plastic work will be converted into the heat. Now, let me give some historical background on the thermal studies on machining. Heat generation in machining was first studied by Benjamin Thompson, who is also called Count Rumford. In 1798, he studied the heat generated in the boring of a cannon and developed the concept of mechanical equivalence of heat. He realized that when we are boring a cannon or gun barrel, in that case lot of heat is generated because machining is done, and this heat generation, he also developed some mechanical equivalence of heat, means mechanical work is done, so heat is generated, but the exact relationship between heat and work was established by Joule in 1850. Joule has developed this in 1850, that relation. We know that nowadays it is called Joule's coefficient, that means which converts this heat to mechanical work to heat. So that this is conversion coefficient. So that Joule's coefficient is used, that is J, and early 1940-50 researchers assumed that material on the two sides of shear plane as separate bodies. So it was assumed that material on the two sides of shear plane as separate bodies, and they find out that how much the heat is going. So they introduced a concept of heat partition coefficient B. That means when I am doing the metal cutting, I may have this type of situation. So this portion is the shear zone. We say that basically shear plane, and this is chip is coming. So suppose here lot of heat is getting generated in this zone. So part of it will go to the workpiece, this part, other part will go to the other part, that is other side of the shear plane. So these are two separate bodies, and that is why in what proportion it will go, that is called coefficient of heat partition. That means we can say B portion will go here and 1 minus B portion will go in the other side, if the total heat is 1. Later on, unified models were used for finding out the temperature distribution. Then people did it as a one body only. Trigger and Chow in 1951 presented an analytical model. They assumed B as 0.1. Trigger and Chow assumed that B was 0.1, that is 10% whatever heat is generated, 10% of it goes into the work and 90% of it goes to chips actually. That they assumed like that. Now, let us discuss a simplified way of finding out average temperatures in machining. Suppose total power consumption in machining is given as P is equal to Fc into V, where Fc is the cutting force and V is the cutting speed. So, Fc into V, no doubt it will be equal to the cutting power, and now this power, total cutting power which we are supplying, is broken down into two components. One is PP, that means power dissipation in primary deformation zone. Other is PS, that means power dissipation in secondary deformation zone. So we have two type of thing. That means why do we require power? We supply that power through some motor which moves the cutting tool, and even job, relative motion it causes. What is that? So that is needed because to overcome the power dissipation in primary deformation zone and also power dissipation in secondary deformation zone. And PS is equal to basically friction force into chip velocity. But the chip velocity in orthogonal cutting can be written easily as R into V, where R is the cutting ratio. This cutting ratio is the ratio of chip thickness to the ratio of uncut to the uncut chip thickness. That means it is R, as we have already discussed in the previous classes, R is equal to Tc chip thickness and divided by T0, that means uncut chip thickness. So this is known, R is equal to Tc by T0, and this, as you know, this always R has to be always less than 1, because due to the plastic deformation there is a thickening of the chip gets thickened. Since there is a thickening, then the length of the chip decreases, and also you know that once the chip thickness has increased, then the chip's velocity. So naturally the chip velocity, because material continuity is there, whatever volume is flowing in the form of raw material, same goes as a chip, So therefore, the cutting velocity, chip velocity also has to reduce by that factor. So therefore, chip velocity is R times V. So if cutting speed is 10 meter per second and suppose your R is 0.5, then the chip velocity will be 5 meter per second. So this is the total power due to friction at the rake surface. Now estimation of average temperature in primary zone is done like that. Suppose we find out PP, that means power expended during plastic deformation is Fc into V minus Fr into V. So temperature rise in the primary deformation zone is given as this. Theta P will be 1 minus B, because beta is the fraction of primary heat that goes to workpiece. Say B may be 0.1. So that means 0.9 will go into the chip. So 0.9 into PP into eta. Eta is the Taylor-Queenie coefficient. This may also be 0.9. So we are interested to know temperature on the other side. That means on the chip side. So that is why I am telling that suppose I had done like this one it is like this here, and this material was going like this. Here the heat was generated, then 10% of this I assume it goes this side, so 90% remains here, and that 90% heat is going in this way. So that will raise the temperature of this chip portion here that we are interested. So rho is equal to density of the material, C is the specific heat of the material, T1 is uncut chip thickness, then this is the volume flow rate, VT1W, that is volume flow rate, and if I multiply by density it becomes mass flow rate, so divide into C. So if we take this total heat divided by mass flow rate into specific heat, then you can get the average temperature rise. So average temperature rise is given by this expression. It is important expression. You can see it will help you to do a rough estimation of the temperature of the chip. 1 minus B PP eta rho C VT1 W. Here B you are assuming 0.1 and eta is also you are assuming, because for most of the materials it is about 0.9. PP you have to find out from this expression, above expression, and rho C VT1, these are the material properties, they may be known to you. W is the width of the cut. So B can also be estimated, although many people have just assumed B is equal to 0.1, but it is found that B is dependent on a non-dimensional thermal number, that is TH. It is expressed as TH is equal to VT1 by alpha. So where alpha is the thermal diffusivity in meter square per second. So what does this thermal number tell? That suppose V is very high, then the thermal number will be very high. T1 is basically uncut chip thickness. If T1 is high, then thermal number will be high. Then similarly you can say alpha is the thermal diffusivity. If alpha is low, then the thermal number will be high. And you can see, you can check that its unit thermal number is dimensionless, because V has got a unit of meter per second, T1 has got the unit of meter and divided by meter square per second. So in the numerator also you get meter square per second, denominator also you get meter square per second, and that is why it is a dimensionless number. So then it has been found that basically that fraction B, that fraction of the heat going B, can be expressed like this: 0.15 ln natural log 27.5 divided by TH tan phi, where phi is the shear angle. So we note from this expression that B will reduce if the cutting speed increases. If the cutting speed is very high, then large portion will only go into the chips. That looks in intuition. Very less amount will be able to go into the workpiece. This is by intuition also. Sometimes you have seen some people can walk on the hot coals, burning fire, they walk. and nothing happens to their feet. They say this is a miracle, but actually what happens, since they are walking very fast, the heat is not able to transfer to their body, and that is this. So same thing happens here, that suppose the cutting velocity is very high, so the tool is moving very fast across the workpiece, then heat is not having enough time to go to the workpiece, so B reduces, and this one. Similarly, but if the thermal diffusivity increases, suppose the material has got very high conductivity, somehow diffusion is very fast, in that case that B will increase also, that is this one. So it is basically thermal number, means B is basically inversely proportional to thermal number. So it tells me many things. Similarly, suppose in the seeing the past expression, if we see even if T1 increases, then also lot of heat will go only in the chip, and this expression is there. So now we want to find out estimation of average temperature in secondary zone also. So Rapier did that complicated analysis that we are not discussing in that detail, but he has provided this expression for a body which is sliding on another body, that expression. So in that case, maximum temperature rise is expected to be 1.13 under root TH T2 L, this is thermal number, and then PS by rho CV T1 and W. So average temperature rise is obtained as PS divided by rho CV T1 W. So average temperature rise is obtained like this, and L by L2 is given by 1 plus tan phi minus alpha, and this one L by T2, basically L by that T2, so that means T2 is the uncut chip thickness. So L by T2 is equal to 1 plus tan phi minus alpha, where phi is the shear angle and alpha is the rake angle, and this expression. So finally, if initial temperature is theta 0, then the final temperature will be given by theta final is equal to theta 0 plus theta p plus theta s. Let us understand this concept by means of one numerical example. Example is like this: determine the maximum temperature along the rake face of the tool when machining mild steel. Given, it has been given that phi is equal to 15 degree, either it has been measured experimentally, that shear angle, or you have done by some analysis, maybe Merchant's analysis or something, and alpha is the rake angle, it is also given, suppose it is 5 degree, V is equal to 2 meter per second, cutting speed is 2 meter per second, or we can say 120 meter per minute, and T1 is equal to 0.2 mm, T2 is equal to 0.4 mm, that means T1 means uncut chip thickness was 0.2, so chip thickness became 0.4, so that means cutting ratio is 0.5, okay, T1 cutting ratio is 0.5, and W is equal to 2 mm, W is the width of the cut, okay, and rho is equal to 7200 kg per meter cube, some type of steel it may be, or some cast iron, and K is equal to 45 watt per meter degree centigrade, this one watt divided by meter degree centigrade, and C is equal to 500 kg degree centigrade, specific is 500, these are somewhat realistic value, may fit in the mild steel, okay, this is mild steel, and theta 0 is 25 degree centigrade, that is ambient temperature, and PP somehow either you measure the cutting force by dynamometer, or analytically you determine that there is some cutting force multiplied by velocity. So supposing cutting power comes out to be 1300 watt, that means you can find out the cutting force and then you can multiply it by the velocity, so you get 1300 watt, and similarly PS has come 270 watt, assume that you know that what is the coefficient of friction. Then you calculate the thermal number. So thermal number is calculated as TH is equal to VT1 by alpha. You have to use consistent unit, use SI unit. So everything is in meter, second, kilogram, etc. So here we put 2 into 0.2 into 10 to the power minus 3 because it is 0.2 mm actually. So into 10 to the power minus 3, convert it into meter and divided by 45 because 45 k alpha is k by rho c. So 45 is k and rho is equal to 7200 and c is equal to 500. So this thermal number comes out to be 32. So since the thermal number is 32, then the fraction of primary heat B is given by B is equal to 0.15 natural log, and this is 27.5 divided by Th tan phi. So plug in those values, 0.15 ln 27.5, 32 tan 15 degree, phi is 15 degree, and this comes out to be 0.17. So what it means that 17% heat in this case is going to the workpiece and remaining 83% is going to the chip. So this we have done. So temperature rise in the primary deformation zone, we know this is the formula, that means 1 minus 0.17, that means 0.83 fraction is going here. So PP was 1300, eta is the Taylor-Queenie coefficient, that is 0.9, rho I have put 7200, C is 500, V is 2 meter per second, T1 is 0.2 into 10 to the power minus 3, and W was 2 millimeters, so 2 into 10 to the power minus 3, and this comes out to be 337.2 degree centigrade. That means this will be the temperature rise in the deformation zone, particularly on the chip side. That means chip has attained basically this high temperature, that means this temperature increase has taken place in the chip. Okay, so earlier temperature was, if it was 20 degree centigrade, then it has become 357.2 degree centigrade, because 337.2 degree centigrade is the temperature rise. And now if we find out this one, that okay, we can find out maximum temperature rise. So we in the secondary zone, there is one formula, L by T2 is equal to 1 plus tan phi minus alpha. So by this formula I can find out what is L, or I can express it in that form. L is equal to this one, I can put the expression here, this is T2 and this one. So theta, it is like that. So in this expression we put the value 1.13 and then we put here value of PS and we put all these quantities, and once we put these quantities here, then we find out this expression rho CV21 and this one, and you calculate, then we find out 552.54 degree centigrade. So maximum temperature rise here is this much, and now temperature rise in the primary deformation zone was already given here. So we add them and we find out the final temperature as theta 0 plus theta p plus theta s, and that comes out to be 914 degree centigrade. So this can be the temperature at the rake surface. Now this is one simple problem by which we have found out that this is the final temperature. Now estimation of temperature distribution also can be done, but one of the best technique is basically finite element method. You have to do finite element modeling, basic equations are there. So as you know that finite element method is a method of solving the differential equations, but there are, you can use many analytical models. We can use Jaeger's heat conduction model due to moving source. That shows that suppose there is a heat source, means certainly that we give Qp amount of heat, and then we have got and this is delta P, and this expression we have got Qp into alpha divided by this one 2k and pi alpha 3 by 2, and if we have got that a width of the chip is 2b, so minus b to b, minus L to L, and 0 to t prime, and this is this t is the time here, and we have written dz dx dt. So, that way we can integrate and we can find out that what is delta p, and as you see that it is exponential type of function, that means with a distance, as the distance from the source increases, then the heat temperature basically reduces, and this will be meter square, suppose alpha is having meter square per second, yes. So, meter square per second into second, so meter square, and that is meter square. So, non-dimensional. So, e to the power whenever there is exponential, so exponential to the power, it should be dimensionless quantity. So, it is consistent, that is what I was checking, and it is done. So, this expression is there. So, such type of expression can be used for finding out the temperature rise. And then you have, so I am not going into much detail beyond that, only thing that you, depending on the situations, you can integrate and do that type of thing, but most of the time nowadays we use, there are finite element packages, by that we find out. Now, I am coming to that how you can measure the cutting temperature. So, there are various methods to measure the cutting temperature. One is I can use some decoloring agent. There are some paint and tapes which change color with variation in temperature. Suppose color changes, then means temperature changes, then color of that tape will also change, and that tape I can paste on the tool or workpiece near the cutting zone. So, heat is generated and we can see how the color of the tape is changing, by that I can estimate. Or we can put some paint also, some paints are there which will change the color. So, before actual measurement by this simple technique, the resulting colors of such paint or tape are pre-calibrated over the range of temperature concerned. That means, suppose we know temperature may go up to 600 degrees centigrade. So, starting from 25 degree to 600 degrees centigrade, we first heat and measure it by thermometer or thermocouple, mostly thermocouple, and then see that how the color is changing, and that color change we have made the noted that suppose it becomes yellow, then the temperature must be 300, when it becomes red, then temperature must be 600, like that we can make a chart type of thing, and next time when we do the machining, then we will be able to know that what must be the temperature. We need not put any thermocouple or thermometer, because putting those things is very problematic. There is a lot of hindrance because of the chip and coolant, etc. Then another method is calorimetric method. It is simple and inexpensive, but it is not accurate enough, and it gives only the average temperature. So, average temperature of the chips can be determined approximately like this. We say volume of chip into density of chip, so becomes mass of chip into C of chip, that means specific heat, so that means total heat capacity, and multiplied by theta chip minus theta W. So, theta chip is the means theta chip minus theta W is the volume of water, and theta W is the maximum temperature of the water. So, water temperature rises how much? So, that means theta chip has given this much heat, that means chip has given theta chip minus theta W heat to this one, that means temperature has been, suppose chip temperature was 300 degrees centigrade, and then after that water has become that temperature of 200 degrees centigrade, then that means 100 degree heat is 100 degree temperature difference is there. So, that means this much heat is lost. So, that is this one, and the water's temperature has risen from suppose 25 degree to 200. So, that means rise in the water temperature is equal to rho VW volume of the water and rho W density of the water, Cw is the specific heat of the water. So, that means basically the heat capacity of water into temperature rise. So, that means heat gained by water must be equal to the heat lost by chip. So that is why this equation is there. This is the heat lost by the chip, V chip into rho chip into C chip, and this one is heat gained by this one. So this we have obtained this expression. So by this everything we can measure. So theta chip can also be obtained. This can be done, and means it can be done. That means this is very useful. Suppose you can have entire calorimetric setup here, and here I may be drilling. Suppose this is drill. So it is doing cutting and it is surrounded by water. So I cannot have access to chip easily, but I can know the temperature of this. So that means particularly in drilling very advantageous this type of calorimetric technique. And using thermocouple principle, that means we can put the thermocouple, tool and work can make one junction, tool and work thermocouple technique, moving thermocouple technique, embedded thermocouple technique, and compound rake tool method. These are the various methods for this one measurement by thermocouple. So one method, suppose tool work thermocouple. So tool work piece is cold at this place, this is this one, and at this place cutting tool is there, so it is hot junction. So hot junction and cold junction, if we make them, so therefore there will be thermoelectric effect. So depending on the temperature difference, here you will see the some voltage, it is in millivolt you are measuring that. So here this is read, and by that, but here you have to properly insulate so that there is no short circuiting here, this type of thing. So it is not so easy, but you can make, many people have done that type of thing. Both the tool and materials have to be electrically and thermally conductivity for this technique. The difference in temperature between the hot and relatively cold junction produces a proportional voltage which is detected or measured in terms of volts by a millivoltmeter. Then there is a moving thermocouple technique. Here if I put there is a chip and it is this one, so it is useful for the study of gradual rise in temperature of continuous chips at low and moderate cutting velocity. Here the workpiece is moving and it is going near the tool. So suppose here I have put a standard thermocouple, I am measuring the temperature here by that thermocouple, but my whole thing is moving also, workpiece is moving. So that means my contact point is reaching near to the tool, and when it is reaching near the tool, then maybe we can see the continuous temperature rise. So maybe we can plot this type of graph also, T versus how much is the distance from here. So the distance from, if we plot in a reverse direction, this may be tool point contact here x, x0 means here, x is like this, then in that case it will be like this. So that means we may study that how the temperature is changing gradually. Then embedded thermocouple technique is also used. Suppose you are doing a milling operation, this is a milling cutter, this is a workpiece, and you can embed a thermocouple, you can make a very small hole and there is a thermocouple bead, then just below the surface you can see what is the temperature. It is useful for milling and surface grinding processes. Temperature is maximum when the thermocouple bead comes very near to the milling cutter, otherwise you can do some extrapolation and you can make some estimate like that. At least qualitatively you can study, even if you have put the thermocouple here, but still you can find out that when the cutting speed is increasing, then this particular temperature is also increasing, although it is not the temperature exactly at that contact. Okay, so embedded thermocouple technique also has been used. Then compound rake tool method also has been used. Here you have hot junction, at this one tool rake surface you can make the hot junction, and the cold junction is here between the workpiece, and this may be non-conductor ceramic tool, but here you have hot junction here, and this is so it is developed to measure the chip tool interface temperature along the rake surface by the thermocouple technique. So it is then infrared photographic technique. Nowadays we have many infrared cameras. This technique was employed by Bouthard in 1963 for determining the temperature distribution in the cutting zone. So the technique involved taking an infrared photograph of the site surface in cutting zone along with a heated strip of known temperature distribution, this one. So we compare that, we take a photograph of that thing. Calibration was used to obtain the temperature distribution in the cutting zone. We take a photograph of the whole thing. So depending on the temperature, your intensity of the photograph will change. So infrared photograph, so intensity will be dependent on the temperature. Points such as X is heated. Suppose this point X is heated as it approaches and passes through the shear zone and finally removed as chip. And points such as Y will cause maximum temperature. So here you will have maximum temperature. Say maximum temperature is at the rake surface some distance away from the nose. Why it is some distance away from the nose? Because by this time the plastic deformation also has heated the chip, and then there is some sliding, so friction also has raised the temperature here. So further has increased, and after that there will be of course decrease in the temperature. Points such as Z remain in the workpiece and heated by conduction as they pass below the cutting edge. So that is what these things are there. Now let us discuss role of variation of different machining parameters on cutting temperature. So machining parameters, work material, that means work material affects what is the specific energy requirement of the material, what is ductility, what is conductivity, what is diffusivity. Then cutting tool materials, thermal properties, chemical stability, wear resistance. Then process parameters, cutting velocity, feed rate, and of course the depth of cut also you can add in this. Tool geometry means rake angle, cutting edge angle, clearance angle, nose radius, they will affect. Environment will affect thermal properties of the cutting fluid and lubrication property, method of the application, how you are applying the cutting fluid, whether you are exactly supplying at that spot and with high pressure, or you are just doing flat cooling, all this will affect. So let us just discuss few things. Role of variation of different machining parameters on cutting temperature. Average cutting zone temperature increases if the cutting velocity increases. So cutting velocity has more influence, you see that it is increasing like that. And with feed also temperature increases, with depth of cut also it is increases. Relative role of variation in cutting velocity, feed and depth of cut and cutting temperature has been shown here. Then average cutting temperature, basically in a way it is decreases with this one, a geometric feature of this one. So suppose this is tool temperature and this may be the cutting temperature, okay. So cutting temperature may be with increasing the rake angle, cutting temperature will decrease only. Why? Because as we told last time also, means in previous lectures, that when the rake angle increases, then cutting force decreases. Cutting force decreases means less amount of power is required. So less amount of power is converted into heat. So it is obvious that if the rake angle will increase, then your machining will be easier and your cutting temperature will be reduced. But rake angle, if it is increases, then average cutting temperature is increasing. But if rake angle has increased too much, then that volume of the tool reduces. That means this one. Suppose this was one tool, but now if it is like this, rake angle has increased a lot. So this tool has become thinner. So that means this will have tendency to increase the tool temperature. So that is why we get this type of behavior. There are two opposing effects. Rake angle increases means less amount of heat generation will be there, but the tool will become thinner, and that's why more temperature rise may be there. So that's why first it decreases and there is one optimum tool rake angle, and after that average tool temperature increases. And similarly the clearance angle. If the clearance angle is increases, naturally the cutting temperature generally may have a decreasing tendency. It may decreases, but but then the tool temperature, because of the same reason, tool temperature will first decrease but then increase. Why? Because if I keep on increasing the clearance angle, this is the suppose we have this type of tool. Okay, this is, say, my tool may be here, right, and this portion. So if this is increasing, then again tool will become thinner, and that is why the temperature will increase. So tool temperature again increases, so there is optimum clearance angle. And cutting edge angle, if the cutting edge angle is increasing, cutting edge angle is complementary to side cutting edge angle in ASA system. That means I am telling that cutting edge angle is increasing, that means side cutting angle is decreasing. If side cutting angle is decreasing, then the tool temperature will increase, because as we told that suppose we were doing the cutting like this, suppose this was the cutting edge, okay, this was the cutting edge, it was very straight, na? And then after that you may have suppose this type of thing, then the total in oblique type of cutting, that edge is inclined, then you are getting more area, so heat is distributed. So that's why in this particular case, if the in this particular case your temperature will be less actually, and here it will be more, no? So that means, but you remember that cutting edge angle is complementary to side cutting edge angle, that means cutting edge angle is 90 minus side cutting edge angle. So similarly nose radius, if the nose radius increases, naturally the cutting temperature may reduce, but sometimes if you know that sometimes if there are other effects it may increase also, but tool temperature will surely decrease because of the more area. Okay, so nose radius also has got that effect. And so this is now so these are the trends with the geometric figure. And now cutting temperature can be controlled or reduced by following method. Now this is proper selection of material and geometry of the cutting tool. Selection of the material is important. Physical vapor deposition or chemical vapor deposition coating of high speed steel and carbide tools help reduce temperature by reducing friction at the chip tool and work tool interface. In high speed machining of steels, lesser heat and cutting temperature developed if machined by CBN tools, as they produce lesser cutting forces by retaining their sharp geometry, by enhancing the thermal conductivity of ceramic tools, that is by adding thermally conductive materials like metals, carbides, etc. in an Al2O3 or Si3N4 matrix, we can enhance the thermal conductivity. Then selection of tool geometry. A large positive tool rake angle helps in reducing heat and temperature generated by reducing cutting forces, but you know that if you increase it too much, then the tool becomes thinner, so that is also not good. And compound rake, preferably with chip breaker, also enables reduction of heat and temperature through reduction of cutting forces. We can have compound rake, that means in here that we can have some rake and after that, after some distance, another rake. By decreasing the principal cutting edge angle, principal cutting edge angle can also be decreased. Then also you can, or in a way increasing the side cutting edge angle. Then optimum selection of cutting velocity and feet combination without sacrificing material removal rate is important. Rate of heat generation and cutting temperature are governed by the amount of cutting power consumption, which is given by PC is equal to T S0 tau S F times VC. F is the form factor. So increase in both feed and cutting velocity raises the heat generation proportionately. Increase in cutting velocity enhances heat generation due to faster cutting action. It substantially reduces cutting forces and hence heat generation by reducing tau S and also the form factor S. So that means velocity has two types of effects. That means on one hand, it of course increases the temperature because heat generation rate increases, but then material also gets softened. So you have to select that proper way. Proper selection and application of cutting fluid is also important. Now what are the cutting fluids in machining? Now Basic purpose of cutting fluid applications are cooling of the job and tool to reduce the detrimental effects of cutting temperature on the job and the tool, lubrication at the tool chip interface and the tool flanks to reduce cutting forces and friction, cleaning the machining zone by washing away the chip particles and debris, and protection of the nascent finished surface. A thin layer of cutting fluid sticks to the machined surface and thus prevents its harmful combination by the gases like SO2, O2, etc. So these are the essential properties of the cutting fluids. It should have high specific heat, thermal conductivity and heat transfer coefficient. It should have good wettability. It should have high lubricity. Wetting and spreading should be there. High film boiling point should be there. And chemical stability should be there. Less volatility should be there. It should not get oxidized too much. Non-toxicity. These are the various properties of the cutting fluids. Now, now here we generally, when the chip is there, so there is a plastic contact zone where the chip usually sticks, and then there is a elastic contact zone where the fluid can easily enter by the capillary action. This thing has been there. Chemicals like chloride, phosphate or sulfide present in the cutting fluid chemically react with the work material under high temperature and pressure. Low shear strength of that reaction layer helps in reducing the friction. For extreme pressure, chloride, phosphate or sulfide type extreme pressure additive is added in the mineral oil or soluble oil depending upon the workpiece temperature. At moderate temperature you can add chloride, then high temperature phosphate and very high sulfide, and this is showing that with cutting velocity that effect is shown here, that means how much is the ratio. That means you maximum high pressure additives benefit you actually get at high cutting velocity. Okay, so that is what this one. And these are the type of cutting fluids. It can be just simply air blast or compressed air. It can be water. It can be soluble oil. It can be cutting oil. It can be chemical fluids, and then it can be solid lubricant, and it can be cryogenic cutting fluid. And we can have, like for grey cast iron, we don't use any coolant usually. For steel, we can have soap solutions also, and soluble oils we can have extreme pressure additive, and then we can have, for aluminium we can use kerosene oil, and for copper also we can have water based fluids, and this is for stainless steel also there are some extreme pressure additive. Most of these coolants are the trade secrets of the suppliers. And methods of application can be drop by drop method, or it can be fluid under gravity. It can be in the form of liquid jet. Nowadays mist lubrication with compressed air is employed, where it is atomized oil is there for efficient cooling, because we don't want to waste too much coolant. It is not good for environment also, and centrifugal effect also sometimes does the job, like in grinding wheels. So these are the methods of this heat up means cutting fluid applications. So this much for today, and in the next class we will tell about this one. Maybe little bit we will recapitulate these topics, and then we will move ahead.